Okay. Hi everyone. We'll be going over the thermodynamics tutorial that I missed last week because I was sick. Um, I'll be coming back shortly because I feel perfectly fine now. I think it was just a small hiccup. But yeah, in any case, let's get started. Um, so yeah, this is general information that you should all know by now. But just to let you all know that we have like I think 3 tutorials left before the last day of class. So for this tutorial, we'll be finishing everything in chapter 5. The next 2 tutorials will be chapter 6 into 2 parts. Then the last one will be chapter 8. And then I'll maybe try and do like for the last tutorial, after the last tutorial, like a final recap tutorial for the 251 final that you'll be having. I just want to know if you guys can let me know when the final is, because I don't have that information, so that I can do a tutorial for you guys. We can do some recaps, maybe go over some past finals, um, and yeah, just go over practice materials, kind of like what we did for the midterm. But for today, we'll just finish up chapter 5. So, like we saw the week before, the tutorial from before, mass flow rate is the movement of mass in a controlled volume, so over time. And you can tell that with the units, so it's kilograms divided by seconds. So it's the amount of mass that's moving in and out of a controlled volume. And this can be calculated multiple ways. You have density times volumetric flow rate. And just to let you know again, volume flow rate is the same thing as mass flow rate, but you replace mass with the volume of a fluid. So let's take water, a particular volume of water is entering a controlled volume, and then a particular amount of water or volume of water is leaving a controlled volume. Um, and that will be like your volumetric flow rate if you were to divide that movement over time. And the units also give you a big hint as to what it is. So it's meters cubed divided by seconds, or feet cubed divided by seconds. So going back to the ways you can calculate mass flow rate, so you got density times area times velocity as well, and area times velocity divided by specific volume, and lastly also volumetric flow rate divided by specific volume. Those are all the ways that you can calculate mass flow rate, but again, you can also mess around with the units so that you would end up with kilograms per second if you're looking for mass flow rate, or meters cubed per second if you're asked to find volumetric flow rate. Two other definitions, just to recap. Steady flow rate is if you have a controlled volume, it means that there is the same amount of mass flow rate going into the control volume as the mass flow that is going out of the control volume. So pretty much mass flow rate going in is equal to the mass flow rate going out, just like as we see here. And with this example, so 2 kilograms per second, 2 kilograms of mass are going into this control volume per second through this pipe inlet, and then 3 kilograms of mass is going through this inlet per second into this control volume. And so if we have steady flow rate, we should have the exact same mass per second going out of the control volume. Lastly, we have steady. Another last definition is steady incompressible flow rate, which I explained last tutorial, but just to go over again, is that the density doesn't change over time and also over distance. So if you were to have, let's assume like a case scenario in reality, like we're not in an idealistic system. And you would have like water going to this pipe and water going to this pipe and then water leaving this pipe inside this control volume. It is very likely that the density of water, so the volume of water in this area, for example, is very different from the one in this area in the center here. But since that would be way too complicated to calculate, we assume a steady incompressible flow rate. So we assume that if we were to have water going to these 2 pipes and then water going and leaving this control volume through this pipe, we assume that the density all over the place is the same. So the volume of water is the same throughout this control volume. And this pretty much means, just like with steady flow rate, where you equate the mass flow rate going in to the mass flow rate going out, is also for steady incompressible flow rate, you just replace mass flow rate with volumetric flow rate. So volumetric flow rate going into the control volume is the same as the volumetric flow rate going out. And then finally, nozzles and diffusers. The most important thing that you need to remember for nozzles and diffusers is that most of the time heat transfer will be equal to 0 unless it is specified by the exercise. Work will be equal to 0. The potential energy will be equal to 0 because you're not having any change of height, you're just going straight. And then kinetic energy is never going to be equal to 0. It's kind of the purpose of these items, in fact. So if you have a nozzle, so the area is reduced, normally you should have an increase in velocity and a decrease in pressure. Whereas if you had a diffuser, it'd be the exact opposite. And again, fun facts, this is the case for subsonic fluids that you'll study later on, maybe if you're taking Aero 464 aerodynamics, that for supersonic fluids, everything flips. So if you had this nozzle, for example, the velocity would decrease, but the pressure would increase at area, at this section. But for now, don't care about that. Just know basically that if in an exercise you encounter a nozzle or diffuser, your heat transfer will most likely be equal to 0, your work as well, your potential energy as well, and then your kinetic energy will probably be the main focus of the exercise. Alright, so let's begin. We have an adiabatic nozzle is having a steady flow of carbon dioxide at 1 megapascal and 500 Celsius with a mass flow rate of 500 kilograms per hour and leaves at 100 kilopascal and 400 meters per second, so that's velocity. The inlet area of the nozzle is 35 centimeters cubed. Determine the inlet velocity and the exit temperature. Okay. Alright. So the way we're going to solve this exercise for the first part, especially, so determining the inlet velocity. Actually, let's go here. Yeah, there we go. So the first step is that we're going to try and find the inlet velocity, and to do that, we're just going to use the classic mass flow rate equation, one of the ones that I listed to you guys. So sorry about that. Here we go. Mass flow rate is equal to area, which is given to us for the inlet, velocity, which is given to us for the oh no, this is what we're looking for, and divided by the specific volume. Now we don't have the specific volume, but here we have carbon dioxide, and like I said, for most gases, you will need to assume that you have an ideal gas. So, and like, there's no other way you could solve this equation without assuming this. So it would be, your specific volume would be equal to its gas constant times the temperature initially, and then divided by the pressure. So that's will equate to 0.1889. That's in kilopascal meters cubed kilogram per Kelvin, and then all of that times 500 Celsius, so that's plus 273 to convert to Kelvin because you're multiplying, so 573 Kelvin, and then you divide that by the initial pressure, which was 1 megapascal or 1000 kilopascal. And all that should be equal to 0.146 meters cubed per kilogram. And then with the mass flow rate, plug in all the values that we know. So we know the mass flow rate being 5,000 kilograms per hour. So we'll need to convert that to kilograms per second. Then we know the area, which is 35 centimeters cubed. We'll have to convert that to meters cubed. And we know the specific volume, which we just found. So if we were to actually change this equation to have the inlet velocity on one side, we would have mass flow rate times specific volume divided by area. And so the mass flow rate is 5,000. But then you should divide that by 60 to convert to minutes, and then times another 60 to convert to seconds. So that will be equal to 3,600. And that'll give us kilograms per second. And then multiply that by the specific volume. We just found 0.146. And then divide that by the area. So 35 centimeters cubed. Actually, just going to do this because there's not a lot of space. Divide that by 35 centimeters cubed, but we want it in meters cubed. So to convert normally to centimeters to meters, you do 10 to the power of minus 2. But since this is squared, we want to convert centimeters cubed to meters cubed, you also convert the 10 to the power of minus 2. You square it. Sorry, it's centimeters squared to meters squared. So you squared also the 10 to the power of minus 2. So that will give you 10 to the power of minus 4. And so you can also do this trick for, like, if you want to convert maybe centimeters cubed actually to meters cubed, you would do 10 to the power of minus 3, and that to the power of 3. Well, you would cube that, and that would give you 10 to the power of minus 9. So that's a nice trick to have under your sleeve. And that will give you an inlet velocity of 57.9 meters per second. That's your V1. There we go. That's a lot better. Okay, so for the second part, that was part A. Now for part B. So for the exit temperature, we're going to use, and that's going to be the case for like 99% of your chapter 5 problem, is just to use the first law equation, what I like to call the elongated first law equation. So good technique you can do, especially when you're starting out these exercises and you're not too sure how to go about them, is you write down the full first law equation. So the change of energy over time is equal to the heat transfer minus the work plus the mass flow rate at the inlet times the specific enthalpy at the inlet, the velocity at the inlet divided by 2, and then the height at the inlet. So that's a z, that'll represent your height at the inlet. And then everything again, but for the outlet, so, and that'll be negative. Usually represented with a E subscript to signify exit, and then I for the initial. Plus G times Z E. Okay, and all that. Now, like we said, there is no change in energy most of the time for nozzles, so that can be removed. There's no specified heat transfer, so that can be removed. Work can be removed because we're not covering any distance with our nozzle. And then what else? Specific enthalpy we cannot remove. Velocity we cannot remove. And then for our change in altitude, we don't have any, so our potential energy components can be removed. So now you're left with 0. Actually, and also another note, these two, the mass flow rate at the inlet is equal to the mass flow rate at the exit. Yeah, here we go. Here it says at the exercise that we have steady flow, and just like we saw before with the steady flow rate definition, means that mass flow rate at the inlet is equal to the mass flow rate at the exit. So just put an equal sign, and that means you have mass flow rate times HI minus HE. And then same thing for velocity, velocity at the inlet minus velocity at the exit. All that divided by 2. And that is your resultant first law equation. And so what do we know and what do we not know? We don't know specific enthalpy in either at the inlet or the exit. We know the velocity at the inlet, we just found it before, and at the exit, it's given to us in the exercise description. So we have 2 unknowns, but these unknowns can be replaced by this equation. So delta H, or specific enthalpy, is equal to Cp integral from T1 to T2, so temperature in the first state to the second state, with respect to dT. Since we are assuming that it is linear for most gases, we can just write it down as the temperature, Cp times the temperature at the exit minus the temperature at the inlet, which is actually the component that we're looking for. So T2 is what we're looking for, and T1 is given to us as 500 Celsius, or 773 Kelvin. And so that's the only missing component here. We know mass flow rate, we know velocities, we know T1, and we just have to plug in everything to find T2. And we actually can remove mass flow rate since we can multiply it on both sides. Yeah, okay, never mind. It's actually HI minus HE, so it's in this integral it would be T1 over T2, and so it would be Ti minus Te, and these two were actually correct. So Vi minus Ve. That's one thing that's very important to make sure you notice, because then this could end up being like a negative when it's supposed to be positive, and then your answer would be completely wrong. And so we plug in our values. Cp is not given to us, but you can find it in your property tables. I believe in the, if not the second page, but the third page. So it would be 1.126 kilojoules divided by kilograms times Kelvin, and that times T which we know actually, sorry. So 773 minus Te, T2, and then plus 57.9 squared minus 4,000 squared divided by 2. One thing to notice is that when you're doing this velocity potential, change equation, so Vi squared minus Ve squared divided by 2, to calculate the change in energy, you would get something in joules. So in order, since here, for example, we're going to get something in kilojoules, we either need to convert this Cp times delta T in joules, or convert this velocity potential change into kilojoules, and that's what we're going to do. We're just going to convert this result that we know we're going to get in joules into kilojoules by dividing it by 1000, or just multiplying it by 10 to the power of minus 3. Just like you would convert from millimeters to meters, we're converting joules to kilojoules. Okay. Just rewrite the equation as it was. So rewrite the equation as it was. 0 is equal to 1.126 times 773 minus T2 plus 57.9 squared minus 4,000 squared divided by 2, and this time I'll make it times 10 to the power of minus 3. And that should give you a result of T2 is equal to 703.4 Kelvin. Okay, and that will be your final answer. So it just really, this is very, very important, is to make sure you either convert this section from kilojoules to joules, because this output will give you in kilojoules, or convert this section, so the velocity potential section, from joules to kilojoules. So either multiply this section by 10 to the power 3, or this section by 10 to the power minus 3 if you want your results in either kilojoule or joule. So this is very, very, very important for these kinds of exercises to make sure. Those are like the two biggest, I guess, errors, is that is forgetting to convert from joules to kilojoules, or joules to or kilojoules to joules. And the other one is making sure that you have everything in the right order. So either it's velocity at the exit minus velocity at the entrance, or the other way around. For like, and that's not just for velocities, that's also for temperatures, just like how you saw I was hesitating there. And same thing for maybe the change in altitude, yeah. So yeah, those are the two big I guess traps that you could get for this chapter. Okay, so let's move on to the next exercise. So just to go over, recap a little bit what we did, and just going over how they did it. For example, in your problem pack, is that initially, same thing. So they found the specific volume. Using the specific volume, they plugged it into the mass flow rate equation to find the inlet velocity. Then they took the elongated first law equation, took out energy change, took out heat transfer, took out work, took out the change in altitude, and you're left with this equation, and also with the steady state. So mass flow rate, both inlet and exit, are the same. Converted the change in specific enthalpy to Cp times delta T, and this time they reversed. We did the inlet minus the exit for both the specific enthalpy and the velocity, but they did the other way around. They did the exit minus the inlet, but in both cases, since you're equal to 0, it's the exact same thing. It was for us to get back to the equation that I used to solve the exercise. You just need to multiply these two components by -1, and you would just get the exact same thing. And then they plugged in everything and found T2 for this result. And yeah, again, warning, when you're squaring velocities or just calculating velocity potentials, you will get your result in joules, and if you want your result in kilojoules, you'll need to multiply by 10 to the power minus 3. Or in another case, you can just multiply this result by 10 to the power 3 to get it in joules, and then you can add those two together. So yeah, there'll be more cases like this for, I guess, like maybe three quarters of your exercises will require you to remember this. Okay, so the stators in a gas turbine are designed to increase the kinetic energy of the gas passing through them adiabatically. Just to recap, adiabatically means that you have no heat transfer, so Q in your first law equation is equal to 0. Air flows steadily, so mass flow rate is the same throughout, into a set of these nozzles at 2 megapascal and 371 Celsius with a velocity of 24.4 meters per second, and leaves the nozzle at 1.724 megapascal and 341 Celsius. What is the velocity at the exit of the nozzles? Okay, so just copy paste that into Paint. There we go. Okay, so let's get started. In this case, what is is the velocity at the exit nozzles. So we don't have to do like in the previous exercise an intermediate, like an initial step where you need to find a one of the missing variables. But if you don't know what variable you're missing, for example, and like the exercise doesn't tell you at the beginning, hey, you need to find the inlet velocity so that you can solve the other question with the first law equation, just do like we did with the previous exercise. Write it fully down. Oh, yeah, select the brush. There we go. Write it fully down. dE divided by dt is equal to q minus w dot plus mass flow rate initial, specific enthalpy initial, velocity potential initial, potential energy initial, and minus the exact same thing, but at the exit, g VE squared divided by 2 plus g E. There we go. And then cross out everything that you know will be equal to 0. So for example, dE dt is equal to 0. Adiabatic, so heat transfer is equal to 0. We're not changing, we're not moving like an object over some distance, so the work is equal to 0. It is steady, so we have mass flow rate initial is equal to mass flow rate at the exit. These two can be factorized. Specific enthalpy we do not know, but it cannot be removed. Same thing for the exit. Velocity at the outlet and inlet cannot be removed. The exercise tells us that it changes, and then the altitude, there is no change in altitude. And now let's check, do we have the mass flow rate? We do not, but we may not need it. Specific enthalpy, in both cases, we do not have it, but as we did with the previous exercise, we can replace it by Cp times the change in temperature, in which case we have the temperature in both states. So no need to, there's no need to pull out the ideal gas equation, for example, or something like that, or the mass flow rate equation to find a missing variable. And then the velocity in both the inlet and exit are also given to us, so we don't need to take that into account. Okay, in this case here as well, we're given pressure, but we don't even need it. So in any of this, we don't have like a ideal gas equation that we would need to use, for example, to find the velocity like we did with the previous exercise. So yeah, so let's get going. So just like with the previous exercise, we're left with this. So mass flow rate times, in parentheses, specific enthalpy at the inlet minus specific enthalpy at the exit, plus velocity at the inlet minus the velocity at the exit, 2. And yeah, it's the exact same thing, except this time your missing variable is not temperature, so at the exit temperature, but the velocity at the exit. So VE is what we're looking for. Mass flow rate also can be divided in both in both sides, and so we don't really need it. And so we're left with the exact same equation as before. That's a C, by the way. It's T initial minus T exit plus velocity initial minus velocity at the exit divided by 2. Make sure again to multiply this by 10 to the power minus 8 to convert to kilojoule. Now you now it's just a question of plugging in everything into into what you know. So Cp is not given to you, but we know that it is stator, gas turbine, or design. It's air. So air is definitely into your property tables, or will be given to you in your midterm as a constant. And you can solve everything. So place VE is equal to, for example, but in this case, if we were to place velocity at the exit on the other side to just make it simpler for us, so velocity initial plus 2 times, because from this, if we were to factorize, or just place it, t, in this case it is a reverse, no, it's not reverse, so ti minus te, and all that to the power of 0.5, or just the square root. Just to recapitulate how we got there, you can just do just some calculus gymnastics. So vi squared minus ve squared divided by 2 is equal to minus cp. You just replace the t2 minus t1 by delta t. Is going to be equal to vi squared minus ve squared is equal to minus 2 cp delta t, and then minus ve squared is equal to minus 2 cp delta t minus vi squared. So put the inlet velocity on the other side, and then multiply everything by -1s, and then square root everything to get ve is equal to 2 cp delta t plus vi squared, and all that square rooted. Just to explain how we got from this equation to this equation. Okay, and then ve is going to be equal to, so we plug in everything, 24.4 meters per second squared plus 2 cp of air, which you find from your tables. Once again, 1.008. This is in kilojoules, kilograms per Kelvin, and then Ti minus Te, which are given to us as 371 Celsius minus 341 Celsius. Since you're doing a subtraction, it wouldn't really change if you would add 273 to both the temperatures to convert from Celsius to Kelvin. So for example, we would just do 371 plus 273 minus, that in parentheses, 341 plus 273 parentheses, and then everything closed, everything square rooted. It wouldn't really make a difference, because then you would multiply this negative with both of these two terms, and the 273 would cancel out, and you would just get 371 minus 341, which would equal to 30 Kelvin. Yeah, so, and plug in everything, and you should get a exit velocity of 247 meters per second. And that'll be your answer. Okay. All right. Yep. So moving on to the next exercise. Yeah, this is the correction that you should get from your problem pack, and it's the exact same thing. Just notice again the 2 megapascals, which we just completely do not use. And yeah, make sure. Oh, in this case, okay, here. This is interesting. So what we could have done here is we multiply by 10 to the power minus 3 for the velocities, and so in this case it would have been 24.4 meters per second squared. That times 10 to the power minus 3, and then plus 2 all of this, and ignore or remove this 1,000, and you would get 247,000 as a result, and you would need to multiply V2 again by 10 to the power minus 3. But in this case, to make things simpler, they just converted this section, which would, if we didn't have the 1,000 joules, would just give us a result in kilojoules. We multiply it by 1,000 to convert it to joules, just to make it a lot simpler. Because you're actually, no, you would get 247. So then it's square rooted. It would have given something with that would be different, and you would need to convert back to velocities. It would be kind of complicated to do. Okay. So let's do this exercise. Okay, so steam flows steadily with a velocity of 10 meters per second into a nozzle at 400 Celsius and 800 kilopascal and leaves at 300 Celsius and 200 kilopascal. The nozzle is not adiabatic, so here it tells us that we have heat transfer, and the heat transfer loss is 25 kilowatts. The nozzle inlet area is 800 centimeters squared. Sorry, keep messing those up. What is the velocity and the volume flow rate of the steam at the nozzle exit? Okay. So again, just plug in your first law equation and see what you have and what you don't have. E dt is equal to Q, which we have is time, minus work plus mass flow rate at the inlet, and all of its energies that you could have, plus GZE, and then minus all the energies that you would get at the exit, plus there we go. dE dt, do we have it? No. Q, do we have it? Yes. Work, do we have it? No. We're not covering any distances. Mass flow rate, are we in steady? Yep, steady. Steam flows steadily. Just like I said here. So mass flow rate at the inlet is equal to mass flow rate at the exit. HI and then HE, so specific enthalpy in the inlet and outlet. Do we have it? No, but we can't remove it. Velocity, we are told that it changes. We're also looking for it, so these are not removed. And then altitude, as always, there's no change, so we can remove it. And then you're left kind of like before. 0 is equal to m dot is equal to specific enthalpy at the inlet minus specific enthalpy at the exit squared velocity at the inlet minus velocity at the exit divided by 2. And voila, again, it's the same thing. Oh, and I forgot one big part is actually Q plus Q, which in this case I multiplied everything by the mass flow rate, which is fine in this case. So this is still big Q dot, and we're gonna leave it as is because here in this case we have kilowatts. Okay, so what do we have? What do we not have? We don't have mass flow rate. We're gonna need to find that. We don't have specific enthalpy, and we're going to need to find that as well. Again, this is also water in a steam state, and so we can't really use that that like simple CP times delta T equation in this case. And then also velocity at the exit we don't know, but that's what we're trying to find. And the velocity at the inlet is given to us as 10 meters per second. Okay, so we are given for the both states, so state 1, state 2, we are given T1 is equal to 400 Celsius, and then P1 is equal to 800 kilopascal, and then for the second state, T2 is equal to 300 Celsius, P2 is equal to 200 kilopascal. Okay. And we know, so steam flows steadily. Okay, steam. Okay, we don't see anything else, so we're going to assume that it stays as steam throughout. And when it says steam, well, actually, in this case, we're going to have to assume that it's superheated vapor. Because if we assume that it was saturated, well, we could have assumed that it was, no. Well, actually, we can just use the tables to figure this out. Figure if it's either a, what they mean by steam is either saturated vapor or superheated vapor. Let's just go check onto our property tables. Property tables, open the tab. Okay, so for the first state, we go down, we know that it is at 800 kilopascal and 400 Celsius. And let's check with 800 kilopascal and 400 and 300 and 400 Celsius. Sorry, my bad. We don't have temperature at 400 Celsius, so let's check. Maybe do we have 800 kilopascal, which we should. So 0.8 megapascal has a temperature of 173.43 Celsius, not 400 Celsius. So we know, since these two don't match up with what the exercise tells us, that state 1 is not in the saturated water or the mixture phase as a saturated vapor. So what we can do is go down into the superheated water into 0.8 megapascal or 800 kilopascal, which is right here, and then at 400 Celsius. So we go along this line. You can't see where the oh, that's perfect. Actually, not enough. There we go. 800 Celsius, go down. So here we see this one is specific volume, which we would need to find the mass flow rate. So 0.6181 meters cubed per kilogram. And then the specific enthalpy, which we also need for 4,155.6 kilojoules per kilogram. We do the exact same thing for oh wait, no, sorry, I took for 800 Celsius, my bad. It'll be these this value, 3,267.1 specific enthalpy, so kilojoules per kilogram, and then 0.3843 for the specific volume. That's right. And then for the second state, we do the exact same thing. We could check again for the mixture phase, but I know already that it's not here. It's going to be here. So we have 200 kilopascal and 300 Celsius, so pressure is 0.2 megapascal. At 300 Celsius would give us this specific volume right here and this specific enthalpy right here. Okay, so now that we have those values, we can go back, no, here, right here. And now the only missing value that we don't have is the mass flow rate. Now, what do we know? The big hint here is that we're given the nozzle inlet area. And we know that there is an equation that can give us mass flow rate with the area. So it would be area times velocity divided by a specific volume. Okay, so do we know area? Yes. Do we know velocity at the inlet? Yes, it's given to us as 10 meters per second, so v1. And specific volume, we found it in the property tables for the first state, so we can use that. So area, remember to convert that to centimeters squared, meters squared from centimeters squared. So again, to convert centimeters to meters, you do 10 to the power minus 2. But since here we're squaring everything, it's 10 to the power minus 4. So 800 times 10 to the power minus 4 meters squared times the velocity, which is 10. And then divided by the specific volume we found for the first state, which is 0.3843. And that'll give us a steady mass flow rate of 2.082 kilograms per second. Okay, so do we have anything missing? Yes, we have the exit velocity, but that's what we're trying to find. So now we can plug in everything into the first law equation and find the answer to the problem. Let me just delete all this. Voila. And voila. Okay, let me just rewrite the equation again. We can write it. Actually, we can write it in this format. Let me do that. It'll be, if we were to have velocity at the exit. Actually, let's write it this way. Written this way, it would be. I guess, yeah, like this, 2 times h1 minus h2 plus v1 squared divided by 2 plus big Q dot. Close the brackets and multiply that by 0.5 or square root of everything. And that would be how to find your VE. Now we plug in everything, 2 to the times the specific enthalpies that we found. So for the initial state, it'll be 3,267.7 minus 3,072.1. Voila. And now what would this give us? This, if you look at your property tables, you see that your specific enthalpy is given to you in kilojoules per kilogram. And then we know that your velocity in the other case is given in joules. As we saw in the previous exercise, it's a lot easier to multiply this section this time by 10 to the power 3 to convert into joules than to multiply the velocity change by 10 to the power minus 3 to convert to kilojoules. Since we've separated both of them. So that's what we're going to do. And we're going to have to do the same also for Q dot as well, because it's kilojoules per second, not joules per second. So then V1 is 10 meters per second squared divided by 2, and then 25 kilowatts times 10 to the power 3. All of this square rooted. Okay. And then this whole section is also multiplied by, I guess, 10 to the power 3. VE would be, you should find 606 meters per second. Okay. And then for the volumetric flow rate, well, you can find that by multiplying the mass flow rate times the velocity that you just found. So why is that? Well, volumetric flow rate is meters cubed per second, and mass flow rate is kilograms per second. Oh, sorry, my bad. Times, not velocity, but specific volume. And specific volume is meters cubed divided by kilograms. And so you cancel out the kilograms and you get meters cubed per second. So V dot is equal to meters cubed, which we found to be 2.082 kilograms per second, times specific volume, which you can find, this is for the exit, so E equal to mass flow rate, same throughout, but then the specific volume for the exit, which you can find for state 2 in your property tables. And if you remember, I think we found it 1.31262, and that's going to be equal to a volumetric flow rate of 2.74 meters cubed per second. Okay. So just on a side note, another way we could have done this exercise is we could have not considered mass flow rate the way we did. So we wrote the equation as such. So if I'm it was like this. So it's a 0 hi minus he plus vi minus ve, both of them squared, divided by 2, and then plus q dot. We could have divided both sides by mass flow rate, and what that would have given us, so let's do it here. That's a really bad line. Mass flow rate, that's going to give us specific enthalpy of the inlet minus specific enthalpy of the exit plus same thing with the velocities. And then what happens with Q dot? It would convert to regular Q, which is instead of being in kilowatts, would be in kilojoules per kilogram. So it'd be like a specific heat transfer, like a specific property. So yeah, actually, let's go over that, because I kind of badly explained that at the beginning of the exercise. But this is the result you should be getting. So we have, I guess, 3 ways of writing heat transfer or work as well. So you have, Jesus, keep forgetting, Q, big Q, Q dot, and then it's the same thing with like work, small work, big W for work, and then W, big W dot. What are their units? So small q, small w, kilojoule per kilogram. Big W, big Q, kilojoule. Big W, big Q with dots on top of them, kilojoules per second, or kilowatts. Okay, so that's the lettering that you should be using, that I'll try to use for the remaining tutorials. But that's how, that's their units. And so you can play around with this. Actually, we saw this at the previous tutorial, where they're giving us hints. For example, like they weren't going to give us mass flow rate, so we had to find work as kilojoules divided by kilogram. We didn't have any other choice. You can play around with this as they say, oh, just give us work, but they didn't tell you which one. So is it specific work? Is it just regular work, or is it work over time? Which one is it? Did they tell us, oh, find work in kilowatts? If they didn't tell you, you can definitely play around with this as much as you want. You don't need to follow like a specific guideline, especially if they're being unclear. But most of the time, they'll tell you, oh, hey, I don't know, find work in kilowatts. Or in the exercise, they didn't give you mass flow rate, so you'd have to use kilojoules divided by kilogram, such and such. Those are like the small hints that they'll usually give you for you to figure out which one is it, the small W, the big W with the Q dot. So yeah, that's just the summary. Recap that. Okay, moving on to the next exercise. So just to recap, see how they did it. Yeah, pretty much the same way. Oh, except this time they multiplied velocity by 10 to the power minus 3. So everything was in kilojoules, and they converted big Q dot to small q. So yeah. Okay, moving on to the next exercise. Yeah, so a steady flow of refrigerant enters a compressor at 180 kilopascal. Steady, they told us that it's steady, so mass flow rate is the same throughout. Has a saturated vapor, so now they give us the state, and that's good. With a flow rate, volumetric flow rate of 0.4 meters cubed per minute, and leaves at 700 kilopascal. The power supplied to the refrigerant is measured to be 2.5 kilowatts. So here, that's one of the hints that I was talking about. And what is the temperature of the refrigerant at the exit of the compressor. So what is a compressor? Usually a compressor is just something that adds pressure or increases the pressure for a substance by reducing the volume. You'll see that a little bit more. Actually, no, you should have seen that in your Rankine cycles. There's a compressor there, and they're used in like your refrigerators. They're used in your turbine engines. They're used everything whenever you hear cooling or compressing gases. Compressors are usually involved. Okay, so let's start with that. Okay, so where do we usually start? First law equation. If you don't know where to start, you just pop in your first law equation, see what you have, see what you're looking for, and see what is missing. So DE, I'll just go quickly with it. Plus EI squared divided by 2 plus it's a little scrunched up, but in any case, I can immediately know that there's no change in altitude, so ignore the potential energy. Mass flow rate is steady, so again, mass flow rate at the inlet is equal to mass flow rate at the exit. Change in velocity, yes, no. In this case, in compressors, usually you won't have a change in velocity. So actually we can ignore this as well. Is there work? We are not moving an object over a distance, so there's no work. Is there heat transfer? Heat transfer, no. No, there's no heat transfer in this. dE dt as per usual is equal to 0, so we're actually just left with 0 is equal to m dot times the change in specific enthalpy, so mi minus he. So it's a much simpler equation. Oh wait, no, yeah, I'm wrong. So wonder if I was wrong there. Work we can't eliminate. It's also actually given to us. So you'll need power. You'll need power to reduce. Actually, yeah. So we're reducing the volume of something. When you're reducing the volume of something, like example for a rectangle, or like a piston, so you're reducing the height of the piston and the cylinder. You're covering distance with an object, so work is not equal to 0. I was wrong about that. Sorry about that. And so, since it's minus W, you can just plug that into the other side as a positive value, and given to us is 2.5 kilowatts. So talking about work, we could leave it as such, and we also have null volumetric flow rate, which we can use to find mass flow rate, or we could just divide everything by mass flow rate, and then you would have small w for so like this. So W this dot is equal to small w is equal to delta specific enthalpy. That could be one way how we could solve this exercise, but in any case, we'll still need to find mass flow rate in order to divide the 2.5 kilowatts by and find the kilojoules per kilograms, the work in kilojoules per kilograms. So we're not going to go that route, but it's one route that you could go through. So how do we find mass flow rate? So we're given volumetric flow rate. How do we find volumetric flow rate? How do we find mass flow rate with volumetric flow rate? We divide. Actually, we could meters cubed per second. And how do we get to kilogram per second? We have something called specific volume, which we've covered a lot, meters cubed per kilogram. So if we were to divide meters cubed per second by meters cubed per kilogram, we would get kilograms per second. So yeah, that's how we're going to do it. So m dot is equal to v dot divided by av. Now, do we have specific volume? We do not, but we know that we are in a refrigerant at saturated vapor initially, and we are also given 100 kilopascal. So let's just put it down. State 1, we have P1 is equal to 100 kilopascal. And another way we can write a saturated vapor is the quality is equal to 1. Now, let's go to our tables, property tables. Go down to, we're not in water anymore, we're in refrigerant at 100 kilopascal. We're in the mixture phase because we are saturated vapor. Let's go with, there we go, pressure. And 180 kilopascal is 0.18 megapascal. And the specific volume at saturated vapor, there we go, is 0.1098 meters cubed per kilogram. And so we just take that okay, well that's completely wrong. Let's take a look at the correction. I didn't see that there. So here, just to go over it, they say saturated vapor. So that means 100% that X is equal to 1. But here in this case, they give us a pressure, the right pressure, so 100 kilopascal. But they say X is equal to 0, and then they have a specific volume that's wrong. Well, it's very close to what we have. So this correction actually is wrong. So just so I can remember that, it's not 0.11 but 0.1098. It's very close. So 0.1098 meters cubed per kilogram. And so we plug everything in. Now we have 0.40 meters cubed per minute. We want that into meters cubed per seconds. So 0.4 divided by 60. And then that divided by 0.1098. Okay, and that should give us a mass flow rate of 0.0604 kilograms per second. Okay. Now, do we have everything else? We have work, we have mass flow rate, we don't have specific enthalpy. We can't, again, refrigerant in this case isn't, it's even worse, it's in the mixture phase, not even as a vapor. We definitely can't use that Cp times delta T equation. So we're just going to use the property tables. We're going to assume that in both cases it stays at the saturated vapor, and using the property tables at these respectful pressures. So state 1 is 100 kilopascal and state 2 is 700 kilopascal. Both cases X is equal to 1. We find the specific enthalpy just like we found the specific volume. Just to quickly do it ourselves. So saturated refrigerant 0.18 at saturated vapor is right here. So 33.45 kilojoules per kilograms. And then the other one was, oh, my bad. No, it's here. 239.71, which is still different from the correction. I don't know where they got their values, but it's wrong. It's definitely wrong. And then for the specific enthalpy in the second state, actually, since we're looking for the temperature in the second state, means that we wouldn't have had to do all of this exercise using the first law equation. They immediately told us that it was 700 kilopascal, and if we assume that it was saturated vapor, so 0.7 megapascal, we could just plug that in as your saturated temperature, since we know that it's in the mixture phase. But in this case, it's not. We can't make that assumption. I mean, that's the whole point of the exercise. They're asking us to find the final temperature. And then they gave us all these volumetric flow rate and a work value. So we can't make that assumption, actually, so I'm wrong. and so we have to find it ourselves. So to do that, actually using the first law equation, we have everything except for the exit specific enthalpy, and that's actually the value we'll use and in the property tables combined with the pressure that is given to us of 700 kilopascal to find the exit temperature. So let's do that here. There we go. Plug in everything to the first law equation. Where is my, there we go. So 2.5 is equal to mass flow rate of 0.0604, and then times HI, which oh, well, I didn't get. I'm not going to use the value from the correction because it's wrong. It is 239.71. Minus HE, which is what we're looking for. So if you were to solve that, everything, I'm going to calculate that myself. The answer is wrong. Actually, let me factorize everything. Is equal to 2.5 divided by 0.0604. So actually this one is minus. This one is plus 239.71. Yeah. Okay. And yeah. So 2.5 divided by 0.0604. Oh, okay. I forgot something that I actually mentioned in the previous tutorial. Power supplied. What does that mean? That means our work is actually negative. So it's not 2.5 positive, it's 2.5 negative. It's our system that's supplying work. If we were to receive work, this would have been a positive value. So it's what we're giving with this process. Then we're losing 2.5 kilowatts. So this actually turns to be positive. And that gives us 281. So HE is equal to 281.1 kilojoules per kilogram. Okay. There we go. All right. So last step, we have specific enthalpy of 281.1 kilojoules per kilogram at the exit, and we have a pressure of 700 kilopascal. So now we're going to pop into our property tables. So again, we see that it's not in the saturated refrigerant due to our equation, which actually we just use this equation to verify if your specific enthalpy was equal to, here it's 0.7 megapascal, was equal to this saturated vapor, which is not, there's a difference in 20 kilojoules per kilogram. So I believe since it's more, we're going to assume that it's superheated. Go down to 0.7 megapascal right here, and our specific enthalpy of 281. So it's in between these two values. So you would have to do some interpolation, and it's in between 40 and 50 Celsius. And so normally interpolating that would give us value of 48 Celsius. And there you go. Okay, so just again a reminder: if the exercise tells you, hey, we're supplying power, we're not receiving power, it's minus 2.5 kilowatts. So actually, if you use this version of the first law equation, it would have been minus, and then in parentheses, minus 2.5 kilowatts, and would have turned into a positive in this equation if you would have kept it in this format. But since we put W on the other side, it remains minus 2.5 kilowatts. Okay. All right. So just to see what they did. So yeah, again, I don't know why they wrote x1 is equal to 0. It's x1 is equal to... That would have been for saturated liquid. But it's x1 is equal to 1, so these two values are wrong. This value is... I mean, I found something very close. Same thing with this guy. I mean, it's very, very close in interpolation here. Okay, so let's begin problem 5.12. Okay, so steam is flowing steadily into an adiabatic turbine. So once again, we have the keywords steadily. There we go, it works. Oh dear. Steadily and adiabatic. Adiabatic, just a quick reminder, is Q, or heat transfer, is equal to 0, and that steadily means that your mass flow rate at the inlet is equal to the mass flow rate at the exit. Inlet conditions in this system is 6 megapascals, 400 Celsius, and 90 meters per second, and the exit is 40 kilopascal, 90% quality, and 55 meters per second. Mass flow rate of the steam is 18 kilograms per second, so that again is throughout the whole system. Determine the change in kinetic energy, the power output, and the turbine inlet area. Okay, so change in kinetic energy. So that's going to go back to one of the equations that you've had to learn, I guess, in chapter 4. Yeah, chapter 4 with the first law equation chapter. And so I guess we can, most of the time it's written as such, KE. Kinetic energy is going to be equal to 1.5. M represents mass, and then V squared. Now, in this case, we're just going to write it in the first law equation format. We could, write this with the mass. I guess maybe in like 1 second. If we were to calculate for 1 second, then mass would be equal to 18 kilograms. Or if we wanted to do this for 2 seconds, it would be 36 kilograms. Doesn't really matter. So in this case, we're just going to ignore it for now. It doesn't. If you remember in your first law equation, the mass is separate. It's out of the parentheses. So in this case, we're just going to ignore it. And since it's a change in kinetic energy, we're either slowing down or going faster. Well, no, in this case, we are going slower from 90 to 55. We can calculate the change. So it would be, again, V at the inlet, velocity at the inlet minus velocity at the exit, divided by 2, and that is equal to 90 squared minus 55 squared divided by 2, and you should find minus 2,540 joules per kilograms. So per kilogram, since we're not, we haven't taken into account mass. But again, you very much can. If you did, when you calculated kinetic energy, you'll get a different value, of course, but you'll get it in joules. And we're going to reformat that actually into minus 2.5, 54 kilojoules per kilogram, because that's going to be useful for us later. Well, actually right now, to find the power output. So to find the power output, we're going to use, actually, let's say this is part A. Part B, power output, just like we did all the time before, first law equation, dE dt is equal to Q minus W plus m dot, and since we know it's steady already, you can just factor m dot and make it so that we have specific enthalpy, specific enthalpy at the inlet minus specific enthalpy at the exit. Same thing. Well, actually, we already know that it's going to be VI minus VE, everything squared divided by 2 for the kinetic energy. So just replace that with what we called it KE. And just plug it in here. Actually, no, this is positive, by the way. There we go. And then the altitude. So you can factor gravitational constant and then Z altitude at the inlet minus Z altitude at the outlet, at the exit. Okay, so what do we cancel? dE dt as per usual. Q, we cancel it. We're trying to find the power output, and that's our big W. Actually, big W dot, Q dot, M dot. We know HI minus HE. We can't remove. There's change in enthalpy, kinetic energy. There's change. There's no change in altitude, so we can remove that. And like a lot of the exercises, we are left with this plus KE. There we go. Now, what do we not know? So we know M dot. Big W dot is what we're trying to find. Specific enthalpy at the inlet and exit, we don't know. We're going to have to try and find that. And then kinetic energy, well, we just found it. That was the first question. So specific enthalpy, we are given hints. Here it's steam, so that can only mean water. And then for the second state, we're given quality. So for steam, we're going to assume that is superheated vapor. So you're going to go into your superheated vapor tables. We're going to go do that in a minute. And then for the second state, 40 kilopascal and 90% quality, that's your mixture phase. So you're going to go into your mixture, saturated mixture tables using 40 kilopascal and 90% quality as your two intensive properties for the second state. And then first state, it'll be 6 megapascal and 400 Celsius. So let's just go ahead and do that right now. Go fetch your tables. Go down, saturated water, the first state was, we'll start with the second state, sorry, 40 kilopascal, so right here, and here is our specific enthalpy, right there. So for the saturated liquid, it will be 317.58 kilojoules per kilogram, and then this is the value for saturated vapor for specific enthalpy. And then using the quality, we'll calculate the specific enthalpy for that state that we are in. Okay. And then for the steam, we were at 6 megapascal, which is a lot. There we go, 6 megapascal and 400 Celsius, so right here. And it's the third column that represents the specific enthalpy of 3,177.2 kilojoules per kilogram. And that'll be our value for H. Now, just like we saw with the previous exercise, we're also going to take, since it's the first state as well, and we're given the area inlet from the exercise, we're also going to take the specific volume of 0.04739 to find the wait, no, actually. Wait, was it the outlet area? It was the inlet area that we don't know. So yeah, we're gonna take the inlet specific volume. We know the mass flow rate at the inlet, and we know the velocity at the inlet, and with all those values, we're going to be able to also answer the other part, the last part of the exercise, which was the inlet area. So let's go ahead and do that. Okay, so specific enthalpy. Let's do that here actually. State 1 is going to be equal to, well, we found it to be HI is equal to 3178.3 kilojoules per kilogram. And then for state 2, we're going to have to use that quality equation of HE is equal to HF, so the specific enthalpy for the saturated liquid plus the quality times specific enthalpy of the saturated vapor minus the specific enthalpy of the saturated liquid, and that should give you a value of 24750.5 kilojoules per kilogram. Okay, and now we have all our values. So yeah, we can go ahead and calculate. W dot is equal to mass flow rate, which is 18 kilograms per second. For specific on W, the initial state 3,778.3 minus 24750.5, and then plus KE, which we found to be 2. It's really small compared to the other types of energies, really. It's quite minuscule. And you should find, and remember, as we just saw right before, this is big W dot, so the value will be in megawatts, so 12.79. Well, you'll find it in kilowatts, actually, so I mean, if it's in kilojoules, it'll be in kilowatts, of course. Watts is joules per second, so kilojoules per second is kilowatts, and then megajoules per second is megawatts. But okay, that's buggy. There we go. So you should find this kilowatts, and then you can change that to 12.79 megawatts. Okay, so that'll be the answer for part B, and then part C, the last section. So just like I said, we know the mass flow rate equation, which is going to be A area times velocity divided by the specific volume. And in this case, we know area. No, area is what we're trying to find. So area will be equal, if we were to change the equation, to mass flow rate times specific volume divided by velocity, and that'll be 18 times, we found specific volume to be 0.047420, and velocity is given as 90 meters per second. That should give you an inlet area of 0.00948 meters squared. Okay, so that was a pretty straightforward equation. Exercise. Delete all that. Oop. Just to see. Yeah, it's exactly the same way. Now you'll notice sometimes in exercises, they'll like switch around, like we did the velocity at the inlet minus the velocity at the exit, because that's how the first law equation is ordered in what we study. But sometimes they switch it around. I don't really know why. But then like later on in the exercise, they take it into account. They put a negative sign over here because they do it the same thing with the specific enthalpy. It's not the inlet minus the exit. It's the exit minus the inlet. But you should get the same answer. So my advice is that you just follow the first law equation given to you. It'll make the most sense. It's inlet minus exit all the time. But yeah, you should always try and be careful with the signs, because then it could be, I don't know, the internal energy. You could find it to be positive, and then kinetic energy you'll find it to be positive, but maybe in some case kinetic energy is negative and you made a mistake, and you subtracted it to the internal energy, then you would get a different answer to what you're supposed to get. So just be careful about that. That's like a typical trap for these kinds of exercises. So moving on. Argon gas, so probably going to assume ideal gas flows steadily. Once again, mass flow rate is the same as always. With a velocity of 50 meters per second into an adiabatic turbine. Adiabatic Q is equal to 0. For heat transfer at 1500 kilopascal and 450 Celsius. So that's our properties for the inlet, or state 1. Gas leaves the turbine at 140 kilopascal with a velocity of 140 meters per second. The inlet area of the turbine is 55 centimeters squared. Jesus. Keep making that mistake. The power output of the turbine is measured to be 180 kilowatts. Determine the exit temperature of the argon. So yeah, I mean that's definitely going to be, once again, your first law equation. Q minus W plus M dot. Again, we know that it's steady, so I'm just going to factor it right at the beginning. Same thing with gravitational constant. And voila. So what's equal to 0? d dt. Q. W is not equal to 0. It's even given to us as a value. Internal energy doesn't change. Kinetic energy, internal energy does change, so we keep it. Same thing with kinetic energy, it changes, so we keep it. And then there's no change in altitude in a turbine, so we don't care about that. Okay, and so once again, I keep forgetting the dots. Here we go. We're just finding again the same equation as last time. Here we go. And our unknowns. What are our unknowns? So we actually don't know mass flow rate. We know our velocities in the inlet and exit. We don't know our specific enthalpy in the inlet and exit. But since we have an argon gas, so in case of a gas, we can make this assumption. So delta specific enthalpy. So the change in specific enthalpy will be equal to Cp times T temperature at the inlet minus temperature at the exit. And I mean, gas leaves turbine 140 kilopascal, velocity 140 meters per second. So I actually just noticed that we don't have temperature at the exit. We do have temperature at the inlet, but we don't have temperature at the exit. So but that is what we're trying to find actually. So it doesn't really matter. So we won't have to do like some idle gas gymnastics. Okay. But in any case, we're given work in terms of kilowatts, so we need to take into account mass flow rate, whether we want to find the small w or not. Well, we're going to have to divide the power by the mass flow rate in any case. So we need to take into account mass flow rate in any case. We can't ignore it. So we'll need to take into steps that will allow us to find it. And how do we do that? Since we have an ideal gas, and we are actually, we're not given the mass flow rate, but we're given the inlet area at the when it enters. We're given the velocity when it enters, and we don't have the specific volume, but we can find it. So just a quick reminder, m dot is going to be equal to area times velocity divided by specific volume. Area we have, velocity we have, specific volume we don't have, but with an ideal gas we can use the ideal gas equation. Specific volume is equal to the gas constants times the temperature at the inlet divided by the pressure at the inlet, which is also given to us. So everybody's happy. So for argon at 450 Celsius, so 723 Kelvin, this is the value. It's 0.281. And that'll be kilopascal times meters cubed times divided by kilograms times Kelvin. That's R times the temperature, which is 723 Kelvin. Make sure to convert to Kelvin because you're multiplying this time. And then pressure is 1500. Okay. And that's going to give you a specific volume of 0.1003 meters cubed per gram. Now we have all the values that we need to find m dot, and that's going to be 55 centimeters cubed for the area, so 55 squared, Jesus, times 10 to the power minus 4, times velocity at the inlet, which is 50, and specific volume, which is found at 0.1103. And that's going to give us a mass flow rate of 2.742 kilograms per second. Okay. Do we have everything? The specific enthalpy, we have work. Yeah, we have pretty much everything. So, actually. Gonna rewrite the equation as such. So yeah, W dot is equal to M dot times CP T1 minus T2 plus V1 squared minus V2 squared divided by 2. And let's reformat this to have it so that it's equal to T2 on one side and all the other variables on one side. To do that, so M dot one side so CP delta T is equal to W dot M dot minus V1 squared minus V2 squared divided by 2, and so it'll be T2 is equal to 1 over CP in parentheses V1 squared minus V2 squared over 2 minus W dot over 2, and we place the T1 on the other side, so it became negative, but T2 is negative, so plus T1. Okay, I believe it should be that way. Okay, let me just go to it again. So yeah, W dot divided by M dot. Okay, so that removes the parentheses. Put the kinetic energy on the other side, becomes negative, so we get this. Then we're left with CP times T1 minus T2. So, oh wait, yep, I'm wrong. Like this. And then this is removed. Yeah, so CP in parentheses T1 minus T2. So you divide everything on both sides by CP. Then you put T1 on the other side, so it'll be like a minus T1 if you were to keep this equation. But since T2 is negative, so multiply both sides by -1, and you should get this equation. But let me know if I'm wrong, actually. So 1 over CP. Oh. Okay, I just realized a big error. When I was trying to find the gas constant, I don't know why I was trying to find CP. I guess I'm still sick. Argon, there we go. Okay, our gas constant, first page, argon will be 0.2081, which is what we used to solve. It was the specific volume to get the mass flow rate. So sorry about that. So yeah, but yeah, all gas constants will be on the first page or just directly given to you. And then CP, well, if it's not given to you, which in this case, when we're trying to find the first law equation with respect to the final temperature, is not given to us. So, and then the correction. So when you're solving this exercises and it's not given to you, and you don't want to go, into the exercise correction because you want to do the exercise well yourself on your own. Just take the one at 300 Kelvin. That's what they did with the correction. Technically, it's wrong. It's not. This is the specific heat for constant pressure at 300 Kelvin. So, but we're at 723 Kelvin, so it's wrong. But just take this one in this case, since I don't think it changes that much. Or worst case scenario, you use. Oh wait, no, yeah, no, you can't. We didn't find it. Okay. So it was from the table. It was 0.5203 times V1, which was 50 squared minus. Yeah, they gave it to us 150 squared and 140 squared divided by 2 minus 180 kilowatts divided by the mass flow rate, which we found to be 2.742, plus the inlet temperature, which is 723 Kelvin. And those are all our variables. Now, just a quick reminder, we can either change the work, which we'll, since it was in kilowatts and we're dividing by mass flow rate, it'll be converted into kilojoules divided by kilograms. So either we convert this to joules divided by kilograms, or we convert the kinetic energy from joules divided by kilograms to kilojoules divided by kilograms. And that's normally the way we go about it. So just multiply this by 10 to the power minus 3. That's really badly written, but just again to reiterate, multiply the kinetic energy change that you find by 10 to the power minus 3, because you convert joules to kilojoules. Okay, and you should find a value of temperature 580.4 Kelvin, and that's your exit temperature of Earth. So sorry a little bit about the mishaps. I guess my brain is not up to par for today, but yeah. Yeah, we're good. Moving on to the next question. Alright. Compressor is used to compress helium gas. Oh, probably gonna have to assume ideal gas from 120 kilopascal and 300 Kelvin to 750 kilopascal and 450 Kelvin. Again, I made the mistake with the previous exercise, but when you're considering compressors, you have, if it were, for example, in a piston cylinder device, something is moving because your volume is changing. So something is moving. One of the dimensions in your control volume is changing. Henceforth, you can assume that there's work. I don't think you can. Actually, no, you could. If you change temperature, you don't have to change the volume. But in this case, it's a compressor. They do it physically, and so most of the time with compressors, you have to assume that there's work. A heat loss of 18 kilojoules per kilogram. So Q is not equal to 0. We don't have an adiabatic process. Is found during the compression process, neglecting kinetic energy changes and probably also potential energy changes. Compute the power input required to maintain a mass flow rate of 88 kilograms per minute. I mean, I'm kind of used to it by now, but first law equation, dE dt is equal to Q dot minus W dot plus M dot. Are we in a steady? It does not stay steady, but we can assume it. They say to maintain a mass flow rate, and that's probably asking for it throughout the whole process. So we're going to assume that. And then specific enthalpy at the inlet minus specific enthalpy at the exit. Kinetic energy and then potential energy. I mean, I'm not going to go over it again, but kinetic energy they said to ignore, and then potential energy we always ignore. So dE dt is equal to 0. Q dot minus W dot are not equal to 0. Okay, so what do we know? We know Q dot. Well, we know it's given in kilojoules per kilogram format, so that's actually Q. And just a quick reminder, to get to Q dot, you multiply that by dot, and that should give you Q dot. And then work is what we're trying to find. Mass flow rate is given to us in kilograms per minute, so we're going to have to switch that to kilograms per second. And then specific enthalpy, since we have a gas, we can do the old classic delta specific enthalpy is equal to Cp T1 minus T2. Okay. Moving on, we'll put W dot on one side is equal to Q dot, or I guess we're going to rewrite that as small q times m dot, and then plus m dot times Cp times T1 minus T2. Okay. And what do we have? T1 and T2. Yes, Cp. Let's check again if the property table gives it to us. They should. They don't give it with a variation of temperature, which is annoying. But they give it at least at 300 Kelvin, which is 5.1926, and that is what they use for the correction. So again, it's wrong. Technically, theoretically. Oh no, it's good. This time it's good. Finally, it's at 300 Kelvin, which is what the table is for. So we're actually good. Cp m dot, we have it. Small q we have, and so we can solve everything. W dot is equal to 18 times 88 divided by 60 to get it into seconds, plus 88 as well divided by 60 to get it into seconds, kilograms per second, times Cp set 5.1926. T1 is 300 minus 450 for the second state, and then solve everything for power. And you should find okay. One thing I need to clarify is we have heat loss. When we have heat loss, it's kind of like when we dissipate power. We're losing something from the system. The system is giving out something to the environment, or whatever the control volume is surrounded by. If we were to gain heat, it would have been positive, but since we're losing heat, it's actually minus 18. So minus 18. So we can see that the heat transfer is making us lose energy, power, sorry, and that the kinetic energy is actually doing the same, because it's 300 minus 450. That's going to result in something negative. So we'll get minus 11 and 68.8 kilowatts. So in other words, what we could say is that this system is dissipating 1,168.8 kilowatts of power. Okay, so that was a simpler exercise. Just, yeah, let me recap real quick. Work, and then heat or heat transfer. If you have the following words, dissipate, or I guess gives out, and here it's loss, or yeah, usually they say loss, then that means you have a negative value. So in this case, it was q, small q, which is going to be equal to minus 18. But let's take for example that we have big W dot is equal to, I don't know, dissipates 5 megawatts of energy. Then it would have been minus, in parentheses, minus 5. So in this equation, it would have been turned positive. Or if we put it on the other side, just like we did before, right here, it would have been minus 5 megawatts. We actually just saw that in one of the previous exercises. But if it's the, if it's the opposite of these words, then it remains positive. Okay. Moving on. I'm going to keep doing this for like 20 minutes and then I'll stop this. It turns into a really long video. Moving on to 5.18. Okay, yeah, no, this one we definitely have to do. Steam enters a two-stage steady flow turbine with a mass flow rate of 22 kilograms per second. Keywords here are already in the first sentence. Steam. Doesn't say steady. 22 kilograms at 600 Celsius, 5 megapascal for the inlet. Steam expands in the turbine to a saturated vapor at 500 kilopascal. So there we go. So saturated vapor for the second state at 500 kilopascal, where 8% of the steam is removed for some other use. The remainder of the steam continues to expand all the way to the turbine exit, where the pressure is now 10 kilopascal and quality is 88%. The turbine is assumed to be adiabatic, so no heat loss or no heat gain. Compute the rate of work done by the steam during the process. Neglect change in kinetic energy. No kinetic energy. They don't talk about altitude change, so no potential energy change. Adiabatic, so Q is equal to 0. Work is what we're trying to find. So if we were to rewrite the first law equation just for study's sake, we're left with this. So that would convert to this. Okay, but in this case, it's kind of particular. We have one inlet, but we have two outlets. So in this case, we have to consider two outlets. If you remember, actually, from your first law equation, I don't write it all the time because it's difficult to write actually with this system. But normally, it's the sum. Yeah. So it's the sum of the internal energy at the inlet minus the sum of the internal energy at the outlet, or well, total energy if you want to consider kinetic energy and potential energy. It's the sum of total energy minus the sum of the total energy at the outlet. So actually, we'll rewrite this way. Okay. Where's my mouse? There it is. Okay, and minus m dot sum HE. Okay, so that translates to m dot times HI minus m dot. There's the first one. So initially, where 8% of the steam is removed for some other use, and then so we'll call the 8% I want to do it the same way as the correction as the second state, and the remaining 92% as the third state. So you're going from state 1 to state 2 and state 3. And you're given properties for each of these states. Okay, so what do we know? Big W dot is what we're trying to find. M dot, we know it is given to us. Specific enthalpy at the inlet is not given to us. Same thing with the specific enthalpy at the exit for both states. But we are given sufficient properties for us to find it in the property table. So recap state 1. Actually, state 1 is 600 Celsius. Pressure is 5 megapascal, and it's also told that we are in steam, so that we're going to assume superheated vapor. We're going to go directly into our superheated vapor tables. State 2. So the steam expand, where 8% of the steam is removed for. It's kind of worded confusingly, but what they mean is that the 8% that is removed is at 500 kilopascal. And we don't know T2. There we go. P2 is 0.5 megapascal. But it is told the steam expands into saturated vapor, so quality is equal to 1. And then state 3. And this, by the way, is, you could say, is, I guess, massive state 1. Say it's like 100%. Massive state 2. Since 8% is being removed, is going to be 8% of the total mass. And let's call it total mass NT. And then state 3. T3 is not given to us. Doesn't really matter. P3, on the other hand, pressure is 10 kilopascal. But inequality is equal to 0.88. So we know it's going to be in the mixture tables. And then mass is equal to 92% of their total mass. So just to quickly go over, state 1, we're going given two intensive properties that are independent from one another, because we know that we're in superheated vapor, so we can say that temperature and pressure are independent from one another, so we can find everything we want. State 2, we're given pressure and quality, two intensive properties, so we can find everything we want. State 3, we are given pressure and quality once as well, and so we can find everything that we want. Where do we find it? Pressure tables, of course, all the time. So let's go ahead and do that. Start with the state 1, superheated vapor. So it was a pressure of 5 megapascal, right there, and temperature of 600 Celsius. And there we go. So we have a specific enthalpy of 3,666.5 kilojoules per kilogram. Then onto the second state of the saturated vapor. So we're going to go into our mixture water tables, and pressure of 0.5 megapascal this time. So right there. And then go all the way to our saturated vapor specific enthalpy, which is 2,748.7 kilojoules per kilogram. And then finally, for the third and last state of 10 kilopascals, right here, it has a quality of 0.88, so we're going to have to calculate the specific enthalpy between the specific enthalpy of the saturated liquid and saturated vapor. Okay. So, right here. Specific enthalpy is equal to 3,667.9 kilojoules per kilogram. H2, 2,748.7 kilojoules per kilogram. And then H3 will be equal to specific enthalpy at the saturated liquid times quality times specific enthalpy of the saturated vapor minus specific enthalpy of the saturated liquid. It should give you a value of 2296.9 kilojoules per kilogram. And so do we have everything? We have... Do we? Yeah, we have everything. And so we can solve this exercise. Actually, one last note. You're gonna... that I forgot is that at our inlet, we have total mass. We start with total mass. At our exit, state 2 and state 3 have different masses. 8% of the mass goes into state 2, 92% of the mass goes into state 3. And so this affects mass flow rate, because mass flow rate is just mass over time, And even though we don't really care about time because it's constant over time, so we could choose the control volume at any time, and it would be the same at any other control volume because it's constant. But the mass from these two exits would be different. So we can say that m dot 2, so the mass flow rate in state 2, is equal to 0.08 times m dot, total m dot, or m dot 1 if you want at the first state. And then we do the same with m dot 3 for state 3. It's going to be 0.92 times m dot 1 in state 1. So that's very important. So we're actually, the way I wrote this is wrong. It should be separated. It should be m dot 2 times specific enthalpy in state 2, and then m dot 3 times specific enthalpy in state 3. Okay. Remove this. Although I remove the entire exercise, doesn't really matter. And so we are left with dot 1 times h1, no, minus, sorry, minus m dot 2 h2 minus m dot 3 h3. Just plug in everything. It was 22 times h1 366.9 minus m dot 2, which is just 0.08 of 22, times 2748.1 0.7, sorry, and then minus 0.92 times 22 times, we found it to be 2296.9. Okay, solve everything, and you should get a work of 20,346 kilowatts. Voila. So that was the only tricky part about this exercise, was just the fact that it separates, pretty much. It's just, you have to make sure that you take into account the sum of the energy change in the exit. So you add the two internal energy changes as we had in this exercise, and also taking into account the mass change as well. Those are the two, I guess, important aspects of this. Okay, so that's going to do it for now. I'm going to stop here. I'll continue later on for our next tutorial with throttling devices and heat exchangers. We'll go over them. And then we'll start with the first part of Chapter 6, which is the Rankine cycle. Okay, so thanks for watching, and let me know again if you have any questions. You can email me here. My email is right here, timclochard@gmail.com, or just directly message me on Moodle. I'll get a email notification of that. So don't worry about me not replying. I'll definitely see your question. All right, thank you.